Okay, we're going to talk quantitative analysis. For some of you, this might be a refresher. For some of you, a lot of this will be new. If it is new to you, hit pause, review the material, rewind, watch different videos, read the book. You have a lot of resources at hand. I'm going to try to keep this as simple as possible. Here is all we're going to cover. It's a lot. I'm sorry. So hit pause if you want to start your outline for your notes. I want to start and talk about data. Data are really messy. And I want to use this example of the introduction survey that you took at the beginning of this class. So in that questionnaire, you were asked to give your height in centimeters. And this is my recommendation to you. Whenever you're collecting data, you want to set up your questionnaire to get the data that you want. And so in this case, it was an open-ended question. And so when you can see on this graphic that some people wrote cm, some people didn't write anything, some people wrote I am such and such centimeters, some people also wrote their height in feet and inches. And so this takes a lot of time to clean up. Thankfully, I was able to use ChatGPT and it cleaned up the data for me. So that was nice. But this is something that you need to think about, that you want to make it so easy for people to enter the data that you want to work with. Another example was in the survey, you were asked how many minutes per week do you spend listening to music? And in this case, being precise would have really helped. So don't have high expectations for people. Even though it was clear in this question, how many minutes per week, you can see that a lot of people answered in hours. Also, some people said it gave ranges. So don't have high expectations for people. Even though I said minutes, people didn't read it. And when you think about it, on my end, cleaning the data, it ends up taking time, right? If someone says about an hour per day, I have to take the time to try to figure that out. I used ChatGPT to get some of that, but I had to do a lot of it myself. So you want to meet people where they're at. And when you have a questionnaire, you want to pilot test it so that someone can say to you, this doesn't make sense to me. So in this case, for example, maybe people think more of their music listening time in terms of hours than minutes. Or maybe it's just hard for people to recall this information at all. And a good example is TV shows. In general, TV shows with commercials are either a half hour or 1 hour. With commercials, that means they're 22 or 44 minutes. So when you say to someone, how much TV did you watch last week? They're generally able to come up with that answer because those blocks of time are in half hours or hours. Music is a lot harder. Question options matter too. By giving people choices rather than letting people type things in, it makes it much easier to analyze later. So in this example, the question asked, what's your favorite color? And gave a list of a bunch of colors. However, the downside of giving options like this is that maybe someone's favorite color was missed. The list wasn't comprehensive. Maybe the list was too long and people were overwhelmed by the time they got to the bottom of the list. Also, some things like, is there a real difference between blue and navy, lavender and purple? And the other thing that's challenging with this, you're still going to have to manually assign numbers in order to calculate mode later. In this question option about how much do students support Husky athletics, this is not a true interval measure because the option choices are not equidistant from each other. But it did allow to have a sort of pseudo interval measure. We're going to use these questions as a basis for understanding, so I also wanted just to refresh your mind about what they were. So what do we mean when we say statistical analysis? This is a method that's used to identify numerical patterns and calculate relationships between and among variables It applies mathematical principles and procedures to analyze, interpret what the data suggest about the phenomenon being studied. Within statistical analysis, we have a goal of trying to be parsimonious. Parsimony is a goal in quantitative research that means that statistical analyses should provide the simplest possible approach that offers the best explanation of the phenomenon being explored. The actual definition of statistics is numerical summaries of data obtained by measurement and computation. And there's three kinds of statistics that we're going to talk about here. The first is univariate statistics, and this is just looking at the values of one variable at a time, like for example, the average age of participants or the average number of minutes listening to music. This is also called descriptives, and we'll talk more about this in a minute. Bivariate statistics examine relationships between two variables. So for example, if age is related to the opinion about the character that appears as options when playing video games. Multivariate statistics are three or more variables. So if people's use of video games in addition to their age might be linked to their desire for a more diverse set of playable options. So univariate analyses are used to describe, whereas bivariate and multivariate analyses are used to explain. So let's talk about descriptives first. Univariate analysis, aka descriptives, this is just an efficient way to describe quantitative data. These organize and summarize the data so that we can understand it better. It's condensed to some numerical indicator that best summarizes the data set. It might be the typical point in a data set or the best representation. The three most common forms of descriptives that we'll see are first frequencies, which are the percentages of each category, measures of central tendency, which we'll talk about in a minute, and then measures of dispersion. Aggregation is another way to understand descriptives. Usually in quantitative research, data are drawn individually. So each person that participates in a survey or in an experiment, we have data about them as an individual. Or in a content analysis, each little piece of communication content. And then when we do statistical analyses, we're not actually that interested in individual answers. We're interested in the aggregate. Aggregation is the combined forms of individual data points about whom or which conclusions are drawn. So for example, let's say there was an experiment where there was subgroups defined by gender identity of the participants. And if men and women respond differently, then the difference is based on the aggregation of the sample by gender. If we don't aggregate and do these summaries of data points and interpretation, this data that we have, like a bunch of rows, just doesn't make any sense. However, by focusing on aggregates, there is a downside that we could fail to notice that if there are exceptional or extreme cases. But in general, with most statistical analyses, we're thinking about aggregation. So frequencies, this is what you're asking about what's going on. This provokes the why question. Frequencies are fundamental to understanding. You need to run the frequencies for every variable that you have. It shows the number of cases in each variable category or level. It's everything that is not a non-missing value. It's usually often displayed as percentages, which percentages, of course, are numbers of cases divided by the total, and this allows us to compare against categories. So here's an example of frequencies from our class data set, and you can see that of those surveyed, that there was reporting that SpongeBob SquarePants was the most popular favorite childhood TV show. So this is all, categorical, nominal data, and people reported on things, and then I just combined them to show the frequencies of occurrences. Measures of central tendency. I know it's confusing because they all start with M. Whatever trick you need from school, use it. These are the expressions of the most common values within a set of values of a variable. The mean, which is also known as the average, is dividing the sum of observed values by the number of cases. So for example, if I have a bunch of test scores, let's say I have 25 students, I add up all their scores and I divide it by 25, and that gives me the mean or the average. The mean as a measure is sensitive to outliers and extreme cases. We're going to look at some examples of this in a minute. Median is the midpoint of a distribution. So you line up all the scores from lowest to highest, and the median is the midpoint. Basically, you divide it in half. It is not sensitive to outliers. We'll look at this again in a moment. Mode is the measure that occurs, or the value that occurs most frequently in the data set. So with those levels of measurement that you had, if you have nominal data, you need to present the mode. If you have ordinal data, present the median. Interval or ratio data, generally you present the mean, but there are exceptions, and we're going to talk about those in a minute. We also need to talk a little bit about skew. We learned about the normal distribution a while back. You can see here that this one in the middle has the normal distribution. Mean, median, mode are all in the middle. If there is a positive skew to the data, so go up and over, you can see that the mean is going to be higher because the mean is sensitive to outliers. If there's a negative skew to the data, you can see that the mean is on the other side. When we have outliers, it skews the mean. And so the median is our preferred measure when we have outliers. We'll look at an example of that in a minute.
So this is a distribution of the heights in our class as reported on the class data set in the intro survey. And you can see that our class range is actually pretty wide, and we are not normally distributed. But the mean, that means the average, height in the class is 172.52. The median is 171.66, so actually not that much below it. And the mode is 154. And so you can see, so remember the mode is the one that occurs most frequently, and you can see that right here, that like kind of right under 160. And these here, you can see that the mean is to the right of the median, but not by much. So it's not necessarily like a huge difference here.
So when do we use mean versus median? This is a really important question. As I said, the mean is sensitive to outliers in extreme cases because it's the sum divided by the number of values, whereas median is not sensitive to outliers. So let's imagine that there's a room of 20 ordinary people, and you walk into this party or this room, and you have to guess their mean and median income. In general, barring something strange going on, we'd probably guess the mean and median to be pretty similar because we're assuming there's no extreme outliers in the room. So let's say that we guess the mean income is $50,000 per year and the median is $45,000 per year. And then a billionaire walks into the room. This person makes $1 million a year. What will happen to the mean income? Remember, the mean is sensitive to outliers. And again, remember, mean would be adding up everything, dividing it by the number of people. So the billionaire's income will heavily skew the mean and will increase the mean significantly. So you take that 50,000, let's say, times 20 people, add $1 billion, divide it by 21 people now, and now you have a mean income of $50 million. Instead of a mean income of 50,000, right? So you can see that this really screwed up the mean, and it's hard to know what's going on in the room because that one billionaire really messed it up. So this is not a good representation of income. But the median, on the other hand, is not going to be affected by the billionaire's income because it's still going to be the middle value. So you can see when you're talking about income in this way that looking at median is a lot more helpful than looking at mean. And you'll notice if you hear on the news that they talk about incomes in Seattle or incomes in the United States or something, they will report using the median. I also want to talk about histograms. These are useful ways of looking at data. When we talked about sampling, we used an example of a histogram from penguin flipper lengths, if you remember. And this is just a way of looking at if the variable is skewed or not, or in what direction, by visualizing the distribution. This is our height in centimeters. The x-axis will display the values of the variable cells, and the y-axis displays the corresponding frequencies. Histograms use bars to represent values, so you can see like here, this is like 151 to 153 in here. With different heights of the bars indicating the frequency that the values appear in that block of data. Okay, so variability. This is, remember we talked about frequencies, we talked about measures of central tendency. Variability is the degree to which values are spread out or are clustered together. The range is just subtracting the smallest value from the largest, and usually we report range fully. So for example, let's say you did a study of people and the age range was 18 to 65. Usually people will report that whole range. Standard deviation is a very important part of variability. Standard deviation tells you how much the individual data values deviate from the mean. It is the average spread of values around the mean. A big standard deviation tells you that something might be up with your data. Things are not very consistent and values are more spread out. A small standard deviation indicates that the values are similar. So as an example, imagine that 5 professors are all grading the same essays on a 1 to 5 scale. And so for essay 1, the professors gave a 4, a 4, a 4, a 5, and a 3. For essay 2, they gave a 2, a 3, a 5, a 4, and a 1. So very different scores. The standard deviation calculation shows that for essay 1, the standard deviation 0.63, not too bad. But for essay 2, it's 1.41. It's higher than 1. It lets us know that the jumps between these away from the mean are really far apart. So in this case, it's a red flag that something's inconsistent in the grading between these professors. So range and standard deviation are super important. If you're reporting mean, you gotta report standard deviation. If you just tell me the mean scores on the test in your class, that doesn't mean much to me. I gotta also know standard deviation to really understand what's going on. Range and standard deviation are also really helpful for noticing errors in a data set. So for example, let's say you do a study for ages and everyone that you talk to is age 18 to 65. But you go into the statistics program and you see the range is 9 to 99. Someone must have entered their age wrong. Or if the standard deviation is huge, something's wrong in your data. So this is useful this way too.
So here we are again with our class data set of heights, and I already talked before about the mean, median, and mode. And you can see our range here is wide, as I said, 154 to 198 centimeters, and our standard deviation is 12.2. So we can think about this range and standard deviation this way. So the tallest person in the class is 198 centimeters tall. The shortest person in the class is 154 centimeters tall. This 12.2 standard deviation tells us how spread out or how different the heights are around the average height of the class. So a standard deviation of 12.2 centimeters means that most people in our class are within about 12.2 centimeters of the average height. So the average height was 172. Most people are within 12 centimeters of that, and you can see that visually. So a smaller standard deviation means that heights are more similar, whereas a larger distribution means that there's more variation in heights among students. And so, for example, if I am grading an exam and the standard deviation is small, that gives me the understanding that most students did fairly similarly to each other. If the standard deviation is really big, that probably implies that there are some outliers and that I'm going to need to look a little bit more closely at them. So let's look at this example with how you all reported how much you support Husky athletics. So we had this on a scale of 1 to 7, and the mean was 4.8 0.4186. The median was 5. So you can see that median means that it skews a little bit more towards the supporting side. The mode was 7, so most people had extremely strong support, and the range was 1.7. With a standard deviation of 1.83, that helps us understand that most students are within about 1.38 points within the median of 5, and you can see that visually. So this is a pretty tight standard deviation. This is not so spread out. There are certainly people who are kind of down here, but there are a lot more people that are.
So recall we talked about bivariate, multivariate, and univariate analysis. Univariate was when we're just looking at single indicators. Bivariate is relationship between 2 variables. Multivariate is relationship between 3 or more. In general, when we're doing explanatory analyses, bivariate and multivariate analyses, we're trying to do one of 2 things. We're either trying to test the strength of relationships, this is also called associations, or we're trying to test differences between means. So we're going to talk about how those are different. We've talked about hypotheses in this class quite a bit before, but I'm going to explain about statistical significance in hypotheses. A research hypothesis is a statement about the relationships among the variables that the researcher intends to study. And then there's this thing called the null hypothesis. And this can be incredibly confusing. Hear me out. Try to follow along. There's also videos on this. The null hypothesis is the opposite of the research hypothesis. It is a statement that is a prediction about what the researcher expects not to find. The null hypothesis is that there's no relationship between the variables or that there's complete randomness. Okay? Researchers use tests of statistical significance to test their hypotheses, and these tests calculate the likelihood that the observed relationships between variables were random or just by chance, that, did this just happen just because? So the null hypothesis is saying that there's no relationship, okay? The research hypothesis says there is a relationship. So we have these types of error that are part of this. Type 1 and type 2 errors are mistakes that are made when interpreting statistical results. Type 1 errors are when someone falsely concludes that there is a relationship when there actually is not one. Type 2 errors are when you don't detect a real effect or relationship, but there was one there. So a type 1 error is also known as a false positive. This is what a case when the researcher rejects the null hypothesis, but the null hypothesis was actually true. Remember, the null hypothesis was that there's no relationship. In this case, with a type 1 error, the researcher concluded that there was a relationship when there really wasn't. So imagine a study where someone is studying, trying to understand if listening to classical music helps academic performance. The null hypothesis in this study is that there is no significant difference in academic performance between students who listen to classical music and students who don't listen to classical music. If the researcher finds a statistically significant difference between those who listened to music and didn't, but the effect is actually just due to chance, they have made a type 1 error. In the social sciences, we use a 5% level for our threshold about if something is just due to chance. Okay? So the researcher will go through a test of statistical significance and ask themselves, is there less than a 5% chance that this relationship is there? A type 2 error is when the researcher fails to reject a null hypothesis that is actually false. This is a false negative. The researcher concludes that there's no significant relationship or effect between the variables when there actually was. So in this case, let's say the researcher failed to find a relationship between academic performance and classical music, but there is a real effect. They may have made a type 2 error by concluding that listening to classical music didn't improve academic performance. In order to avoid type 2 error, you have to have a good sample size so that you can actually see the relationship.
When we talk about making a statistical inference, this is really just us making an educated guess about what is going to happen in a population based on what we see in our sample. It's a process of making decisions about ideas or hypotheses based on data. It's sort of like trying to find out what's in a giant jar of jelly beans by just grabbing a handful, right? If you have a few white ones and a few yellow ones in your hand, you're going to probably try to make some conclusions about what's going on in the whole jar. Within this, we use tools like p-values and confidence intervals to help us make these inferences. P-values tell us how likely we are to see our results, or more extreme results, if there's actually no effect in the population. It's not the probability that our hypothesis is true, but a small p-value, like less than 0.05 or 5%, suggests that our results are pretty unlikely to be due to chance alone. Statistical significance is related to this. When we say a result is statistically significant, we're saying that it's unlikely to have occurred just by chance. But remember, statistical significance doesn't always mean practical significance. A tiny effect could be statistically significant in a really big sample, but it might not actually matter that much in reality, in practical terms.
Researchers use these tests of statistical significance to test their hypotheses. These tests calculate the likelihood that the observed relationships between variables were just random, or if there is a real relationship between variables. P-values are measures of statistical significance. We calculate them with statistics software. In your textbook, they talk about SPSS, but you can also use Excel, Google Sheets. You can also calculate it by hand. P-values represent the probability of obtaining results that are as extreme as what was observed, or if there's no real relationship between the variables. As I mentioned a moment ago, there's a long-standing tradition in the social sciences of using a 0.05 significance level, which means that there's less than 5% chance that the results were due to random chance. We usually report results as less than 0.05, less than 0.01, or less than 0.001. The lower the p-value, the more certainty we have that it wasn't just due to chance. So with p being less than 0.05, it means that the likelihood of finding the relationship between variables that were observed in the study, where there is no such relationship in the population, is less than 5 in 100. So if a researcher obtains a p-value within this range, less than 0.05, they can reject the null hypothesis. So the goal is to reject that null hypothesis. That, again, that was the hypothesis that said that there's no relationship between variables. The smaller the p-value, the more plausible the research hypothesis is compared to the null hypothesis. If this was a lot for you, hit pause, listen to it again. There's also a video on this that explains it in a different way. It is hard. I know. So how do we get to statistical significance? You need to have a good sample size. You have to have a strength of relationship between variables. And with larger sample sizes or stronger strength of relationships, you have a higher likelihood of finding statistical significant relationships between variables. I do want to warn you, though, that statistical significance does not necessarily imply practical or clinical significance. Practical significance means like that it doesn't actually really matter. So imagine that a study shows a statistically significant reduction in depression after a treatment, but the effect is really tiny and the treatment costs millions of dollars and it's really hard for people to go through this treatment. So even though there was a statistical significance, this study might not have practical significance because it might actually not be worth doing. Clinical significance, let's give an example of there's a new medication that lowers blood pressure by a few points, but the medication has a bunch of side effects. Even though the study might have shown that it's statistically significant, it's not actually clinically significant because doctors aren't going to use it because of all these side effects. I also want to mention that inferential statistics technically should not be used in a non-probability sample because inferential statistics really require you to have a random sample that goes along with a normal distribution. Non-probability samples are less likely to be random, obviously, and they're less likely to have a normal distribution. All of these analyses assume a normal distribution. So, in reality, we still do this, but you have to be much more cautious in the assertions you're making when you are trying to use inferential statistics on a non-probability sample. So, a good hypothesis has to be falsifiable. That means it's testable. It's falsifiable if it can be potentially proven false through observation or experimentation. So, for example, all swans are white is a falsifiable statement because it can be tested through observation. There is a God who created the universe is not a falsifiable statement because you can't test or observe that. Good hypotheses need to also be significantly specific, concrete, and clear in order to be tested. Research questions are okay, but in general, we prefer hypotheses. Research questions are only used when there isn't enough prior knowledge in your literature review or if prior research findings contradict each other. But if you're going to do a study that's quantitative, you really want to try to have a hypothesis. And on top of that, you want to try to have a directional hypothesis. Non-directional hypotheses, they're also called two-tailed hypotheses, are when the researcher predicts that there will be a difference between two groups or a relationship between two variables, but does not specify what direction the difference or relationship goes. You want to try to have a directional hypothesis since it's more precise. So a directional hypothesis would be as more television viewing increases, fear of crime increases. A non-directional hypothesis would just be the amount of nukes consumption will be related to fear of crime. Or comm majors and poli-sci majors will have different LSAT exam scores. But you don't predict any particular direction that they go in. Try not to do that. Okay. Again, bivariate and multivariate analyses are used to explain. We look at associations and differences. Important to know is that the type of statistical analysis that you can do depends on two things. One, the hypothesis you have. Is your hypothesis implying association, or is it about comparing differences between groups or interventions? And the level of measurement of your variables. Only some tests can be done with some levels of measurement. So we're going to go through them, and it's going to be really important that you learn what levels of measurement go with which test. So first we're going to talk about associations, and then we're going to talk about differences. The primary association that we understand is called correlation. People say this casually all the time in everyday speech, but it does actually have a statistical meaning. The change in one value of one variable is associated with a change in the other variable. A correlation requires two continuous variables. In a correlation, you compute something called a Pearson's R. This Pearson's R tells you the direction, positive or negative, and the magnitude of relationship. It is very confusing for people, but Positive relationship means that both variables are going in the same direction. Negative relationship means that the two variables are going in two different directions. Okay? I don't know how to get it stuck in your head, but positive just means same direction, negative means different direction. Pearson's R also tells you the magnitude, meaning the strength of the relationship. So, direction of relationship, as I said, a positive R. As X increases, Y increases. So here's an example. With more hours spent revising, which is British English for studying, your exam score goes up. Hours spent studying, exam score goes up, positive. Negative R, as X increases, Y decreases. X, flu shots given, positive, like it goes up. People with the flu goes down. So this is a negative correlation because flu shots are the things that are increasing and people with the flu is the thing that is decreasing. Okay? Magnitude of relationship, this Pearson's R ranges from 0 to 1, specifically -1 to +1 with 0 in the middle. The further from 0, the stronger the relationship. And the general rules, obviously 1's a perfect relationship. 0.7 to 0.9 correlation is a strong relationship, and that's what we want. 0.4 to 0.6 is okay, it's a moderate. 0.1 to 0.3 is weak. It's nothing to get that excited about. So let's look at an example of correlation. This is from this website. It's kind of a joke about things that are correlated. It's really important to know that correlation can tell you that these two variables are related, but correlation does not tell you that one causes the other. You don't know. Is it possible that a third variable is the actual cause? The relationship is spurious. It also doesn't tell you the independent variable versus the dependent variable directionality. In general, we know that independent variables should come first in time before dependent variables, but sometimes in life, things happen at the same time. So for example, the divorce rate in Maine correlates with consumption of margarine, which is like this fake butter. And it's correlated pretty high. The R is 0.99. It's almost a perfect correlation, and you can see this in the chart, right? So obviously these two things have nothing to do with each other, right? And there's no independent or dependent variable, but this is just to go to show you that really anything can be correlated. Here's number of people that drowned by falling into a pool, correlates with films Nicolas Cage appeared in. I mean, this is ridiculous, but it's correlated 0.66 repeating. So this website is pretty funny. You can go to it if you search for spurious correlations, or I guess this guy's name's tigervegan.com, Tyler Vegan. You can check it out. But the really, really important take home here is that correlation does not equal causation. Sing it from the rooftops, tell people this is not the case. Correlation just means that these variables are related. That's it. Another part of correlation is R squared. R squared is the coefficient of determination. This is a correlation where you actually do have an independent and dependent variable, unlike the examples that we just talked about. R squared shows how much variation is in variable A, the dependent variable, that's explained by the variation in variable B, the independent variable. This is often used to indicate the strength of relationship. Again, it doesn't indicate causality, just the strength of relationship, but there is an independent and dependent variable. So we use it to explain variation. So in this example, if age and earnings have a correlation of R as 0.60, then R squared is 0.36, which means that we can say that 36% of the variation in the earnings variable is explained by variation in the variable age. So that means that the rest of it is not explained by age, and that means that there are other variables that contribute. Or in another example, let's say you're doing a study of work-life balance and job satisfaction. The R squared indicates the extent to which work-life balance can be explained by differences in job satisfaction. A low R squared indicates that other factors might be influencing job satisfaction. Control variables, we've talked about this a little bit before when we talked about experiments. Control variables determines if a relationship between A and B holds up if a third variable is introduced. Usually, this is a variable that is held constant to isolate the effect of the independent variable on the dependent variable. So, for example, imagine a study that looks at income as a dependent variable and how much education someone's had as the independent variable. We would assume with the more education someone's had, they probably make more money. But age is an important control variable in this study because people that are older are also going to make more money, right? And it affects the impact that education has on income. So age also influences income. You have to hold it constant because otherwise it could confound the relationship between educational attainment and income. The other form of association that we talk about quite a bit is regression. This is when there is more than one independent variable. It is a multiple regression test. This is how we explore multiple variables predicting a single dependent variable, and they tell you how much each predictor variable and each independent variable entered into the model contributes to the dependent variable, both one by one and also combined. The simplest form of regression uses all continuous measures. Remember, correlation that we just talked about was all continuous measures. If you have a categorical variable that you want to put into regression, you have to do this thing which is called creating a dummy variable, where that categorical variable, one value of it, let's say it's like blue eyes versus brown eyes or something, is given a 1 and the other values are given a 0. So you basically make it a continuous variable that is 1 and 0. In a regression, beta coefficients, you can see this little character beta, for each variable are the measures of the strength of the effect of entering each variable into the equation. The higher the beta coefficient, the stronger the predictor is, and each beta has its own associated significance level. So here is a regression study I did many years ago that looked at internet use. I looked at the age, their household education, or their household economic situation and their education. This beta score, age, was negatively related to using the internet, and it was significant. Their economic situation was slightly significant, or was still significant, but a little bit less, and education was pretty highly related. So each of these was a contributor, and then there was an overall measure as well. That actually is that R-squared that we talked about. If you have a ton of independent variables, you often will enter these as blocks, and this is called stepwise regression. Each block entered has its own R-squared, and the subsequent blocks build on it. And what's really interesting is that stepwise regression is actually really rigorous because that last independent variable still has to explain some of the variance, even though all the previous variables already ate it up in the model. So there's videos, textbook, you can read more about this, but now we're going to move on to talking about differences. Differences are testing the means between 2 or 3 or 4 or whatever, different groups, or manipulations, especially if you're doing an experiment. The goal is to compute mean scores of the dependent variable for each category of the independent variable and compare them. If you're doing an experiment, you're definitely going to be doing a test of differences where you're comparing means. But you could also take other data that's not experimental and do test of differences. So for example, do children in divorced families do worse in school than children in non-divorced families? You get all the kids' GPAs, you sort them by divorced family or not, and you compare the average GPA. This isn't an experiment. You're using existing data, I guess you have access to, and doing a test between differences. But again, if you're doing an experiment, you're definitely doing a test of differences. So there's a couple different differences test. The first one is called a chi-squared. Even though it's spelled C-H-I, you pronounce chi like the word sky. And that X there is the Greek letter chi. Chi-square test allows you to look if there are actual data differences from a random distribution. A chi-square test requires you to use two categorical, usually nominal, variables. You're going to see if there's significant associations between those variables. We want to know if there's a difference in the distribution of responses or frequencies among these two groups. In a chi-square, you calculate the expected frequencies for each category, assuming that there should be no difference significantly between the groups. Then you look at the observed frequencies and you compare the expected versus the actual. So we tend to use a crosstab with this, and let me show you an example. So in our class data set, I asked you if you played soccer on a team as a kid and also about people's eye color. So in this case, this is a crosstab. You can see these are the class eye colors. This is no, I didn't play soccer on a team. This is yes, I played soccer on a team. And this is how many of you, in actuality, the observed frequencies for each eye color category and each playing soccer or not category, how many ended up in each cell. But then I calculated this expected frequencies. And how we calculate expected frequencies, you can see for this example, this is for didn't play soccer and brown. I took the total number of people with brown eyes, I multiplied it by the total number of people that did not play soccer, and then I divided it by the total number of both. And this gives me the expected frequencies. So in this case, it was expected that 20-ish people would have brown eyes and say no, etc. So if you look at the expected versus the observed, you can actually see that there were some unusual differences. So for example, up here, hazel eyes. In reality, one person with hazel eyes didn't play soccer. 5 people with hazel eyes did, but the expected were 2.6 and 3.4. So, just as an example. And so what was pretty interesting, this calculation is actually looking at the differences between the observed and expected with, squared. And you can see, like I said, this hazel was a little different. Blue eyes was a little different than expected. In this case, the p-value was 0.29. And remember, with our p-values, we want them to be less than 0.05 because that would mean that there was a greater than chance likelihood that the relationship actually was significant. In this case, it wasn't, but also we wouldn't expect there to be, right? Like there's no theoretical reason why playing soccer and eye color would have anything to do with each other. I just had to use it for this example because it was the easiest categorical variables to use. The other form of differences in the next way to think about this is called t-test. T-test allows you to compare two categories, sample means, against a continuous variable. Okay, so this is a categorical variable that has two levels against a continuous variable. There are independent and dependent t-test. An independent t-test is calculated based on the size of the two groups and the amount of variation between the two groups. So these are groups that are not related to each other at all. A dependent t-test, the groups are closely related to each other. Like it would be like two parts of a partnered couple or a kid and their parent or something, that you would expect the results to be really similar to each other. This is also the test that we use when we're testing the same people over time. Like if we were testing their measures on some sort of IQ test at one point and then at some point in the future. Okay, but don't worry too much about this independent and dependent. Remember that t-tests are two levels of a categorical variable looking against a continuous variable. So for either independent or dependent test, that grouping variable is the one that divides the sample into two groups. It's usually going to be a nominal. So for example, imagine you had an experiment and you had a control condition or a treatment condition. This is a variable that divides the sample into two groups, people that were in the control or people that were in the treatment. It's a nominal level measure. Because t-tests determine if means are different in the first group versus the second group, the dependent variable has to be continuous, interval or ratio level, so that the means make sense. So in this case, I looked again at this soccer, having played soccer, yes or no. So 41 of you said that you played soccer as a kid, 36 of you said you didn't. And then I took this Husky athletic support. Now, this is not a true interval measure, but we're treating it as such, as you've read in the book, that in communication we tend to treat it as such. So I did a t-test and I said, okay, is there a difference between people that played soccer and didn't play soccer in what they said their support of UW Husky athletics is? And in fact, there was a significant relationship. This p-value here is 0.00. Super interesting. So if we look at this, we can see that, so green is people that played soccer and blue is people that didn't play soccer. And you can actually see that people that played soccer were much more likely to be on the upper levels of support of Husky athletics, and the people that didn't play soccer were much more likely to be on the lower levels. So this was interesting. So soccer is a nominal variable, remember. This support is a fake interval. And yeah, we calculated this as a t-test. So that was pretty interesting. There is a significant relationship between having played soccer and Husky athletic support in that there is a significant difference between those who played and didn't play. The last test we're going to talk about is ANOVA. ANOVA stands for Analysis of Variance. ANOVA is the t-test older sibling. ANOVA tests differences between 3 or more categories sample means on a continuous variable. So t-test has to be 2 levels, in that case played soccer didn't, and then on any continuous variable. ANOVA, 3 or more. We're going to focus on one-way ANOVA. There's a lot of different kinds of ANOVAs, but we'll use it one-way ANOVA for this example. So in this example, I looked at that eye color measure against this pseudo interval measure of support for UW Husky athletics. So you can see here that when we went across eye colors and support, that there were some notable differences, and you can look here and you can see like, you know, the differences are a little bit different. Now, what's really important is that we had a ton more people in this class overall with brown eyes than any other color eyes. So it's not really a fair comparison. However, the p-value was significant, which is shocking. I think that the low numbers of some of these eye colors impacted the result, but it did end up having a significant result. So there's no theoretical explanation for it, but it did exist in here. But so you can see that, again, that the eye color is a nominal variable that had more than 3 categories. We had, in this case, 5. And the continuous measure is a pseudo-continuous measure of support for Husky athletics. So again, a t-test is 2, like soccer, yes, no. ANOVA is 3 or more, and this is different kinds of eye color.